Stationary state probability density. Welcome to LIB Academy. In this video, we are going to prove that the probability density function for a stationary state is not dependent on time, that is using the separable wave solution. This video is also part of my quantum playlist, so feel free to check others out. In classical physics, from Einstein's photoelectric effect, the probability of finding a photon is equal to the amplitude squared. It's proportional to the amplitude squared. So the equation that we've been working so far on in quantum mechanics, so far the equation that we've put in effort to prove is the wave function solution, which is psi of x t equal psi of x e to the power minus I et slash a cross. In our previous videos, we look at how we came around this, how we got this wave function here. And this is what we are using now to be working on. Now we are still progressing in quantum mechanics. Now that we have the wave function, trying to predict the position of an electron in quantum mechanics. Born came with an idea. Born came with a theory that if in classical physics, the probability of finding a photon equal the amplitude squared, then the square of the wave function should have something to do with the probability of we finding an electron in space. So the probability of finding a photon can also be called probability density. Probability density. So when you come to quantum mechanics, the probability of finding an electron in space, if that is only our system, is the wave function squared. And that is what we are going to do in this video, to prove that the probability density for a stationary state can just be written in terms of the special part of the wave function, just like this. So our separable wave equation, which is psi of xt equal psi of x e to the power minus I e t slash h bar, and we said that this is our special part, the special part of the wave function, and this is the time part of the wave function. So for probability density of the wave function, so let's say our probability density, let's represent our probability density by p of x and t. It should be equal to the wave function squared, right? So that means we multiply, the wave function by itself twice. And one thing you need to know in quantum mechanics is that this wave function right here, the wave function right here, is complex. But probability must be a real or positive number. So in order for us to represent a real physical system with this wave function, we need to multiply the complex number by its conjugate in order to be able to use it to represent a real physical system. So how do we do that? What makes the wave function complex is the presence of I here. So it makes the wave function complex. We are going to take the complex conjugate of the wave function so that that term will cancel out. So let's represent one of the wave function as psi star, indicating this is the complex conjugate of the wave function. Complex conjugate of the wave function. So now let's proceed. So psi of x, psi star, we can just write it of x e to the power, and the conjugate, taking a complex conjugate means what term is right here, the complex conjugate will take the opposite of that term. Here the term, the exponential function has a power of minus iet over h bar. So if we take the complex conjugate, it's going to take plus e to the power iet over h. So the complex conjugate is going to take plus iet over h bar multiplying psi of x e to the power the normal, exponential part without changing the sign. So taking complex conjugate means that the sign of the exponential function will change for the other part of the wave function, which is the complex part of the wave function. So now, if we have exponential functions, a multiplying, e to the power a multiplying e to the power b, you can simplify it as we just add the powers, e to the power a plus b. So that is what we are going to do here. So let's group the exponential part. So we have psi star of x multiplying psi of x, and we have the exponential function to be here. So now we are going to write e to the power positive I e t over h bar, then plus minus I e t over h bar. And you know that plus and minus, that means we are going to get negative I e t over h bar. And at the end of the day, this is what we are going to get. Psi of x, this is psi star of x, but they are just the same though. Taking the complex conjugate doesn't mean that this wave function is different. We are just finding a mean to get away with the exponential, the complex part of the wave function, which is right here. So e to the power 0. And e to the power 0 is the same as 1. So there's no need to write it. So the reason why we're taking the complex conjugate was to get rid of the exponential part, the complex part of the wave function. So now that is gone, we are going to get an absolute. You can just write this as absolute psi of x squared. If we are still confused about the complex part of the wave function, if we have a plus ib as a term, let's say we have z to be equal to that. Here we have a real part. This is the raw part, and this is the complex part of the wave function. The imaginary part of the wave function. Get it? Where we have the I to be there. So if we have psi of x e to the power I et over h, so this will be the raw part of the of this expression, and this will be the imaginary part of the expression. where we have the I to be there. So looking at the general wave function, which is here, is this is the raw part, which is a special part, and this is the imaginary part. So now we are proving that probability density can just be written in terms of the wave function. Probability density, let's say p of x and t, can just be written in terms of the square of the wave function. Because if we take the complex conjugate, the exponential part will cancel out. And don't forget, this is only for the separable wave solution. If we are looking at this wave, I mean, this general formula here. Sorry, it's not with this. It should rather be this. So in summary, anytime you hear probability density in quantum mechanics for now, probability density should be equal to the wave function squared, psi of x squared. It can also be represented as psi star multiplying psi. So any of these can be used to represent probability density. The star here means taking complex conjugate, right? So that is it for this video. See you in my next video for expectation values, Hamiltonian square, and then calculations, I mean normalization of the wave function, which will involve a lot of practical problems. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.